Okay, folks, we're going to start. It's 10 past the hour. So, morning, everyone. Sorry, I gotta ask you guys we want to start. Yeah. Okay, so how was M2? So we haven't met in a while. Was it easy? Yeah, okay, good. A bit stressful? Was it stressful? Yeah. Yeah, M2 was designed to stretch you a little bit because it's an open-ended milestone, but I hope you guys had fun. And now we're going to talk today about M3, which is kind of building on top of what you learned in M2 and doing some algorithms, which is kind of my favorite part of this course, you're learning how to do different things with graphs. Okay, so milestone 3 basically is divided into two portions. One portion is algorithmic, where you're going to find the shortest driving time or the shortest path between two intersections. So imagine that you're driving in Toronto and you want to go from Spadina and College to, for example, Bloor and Yonge. So you're going to find the path that gives you the minimum travel time to go, assuming that you're driving at the speed limit, which is the most optimistic speed. Okay, the second portion of the milestone is more user interface like you did in M2, and we're going to talk a little bit in a bit about what you need to do there. So the milestone is worth 15%. 6% are coming from the unit tests, similar to what you did in M1, where you're going to test you again for functionality, robustness, and performance. Okay, so basically we want to make sure that you're finding at least a path, which everyone should get, and then that path should be the shortest driving time, and you're doing it with the lowest CPU time possible. Okay, the second portion, the UI, is worth 7%, and that's basically up to the judgment of your TA. You're going to demo to your TA and see if you completed all the features required for that UI. And the last 2% are basically similar to what milestone 1 and milestone 2 did, where basically code style, project management, make sure that you're dividing your tasks evenly and updating the wiki regularly, etc. So the due date is going to be in, oops, that's Sunday, not Saturday. It's Sunday, March 23rd at 11:59 p.m. So it's in less than 3 weeks. You still have a little bit of time, but it's we're going to see that, yeah.
When did you say it was due?
It's Sunday, March 23rd.
23rd.
Yeah, this is a typo. It should be Sunday, not Saturday. So yeah, try to start early. This is a big milestone, and it's we're going to see that you will be able to divide it in parallel among the 3 team members. Okay, so the algorithmic portion, as we said, that we're going to find the minimum travel time to travel from one intersection to another. And this travel time is basically calculated through a formula that you're going to implement in one of your functions for M3. It's basically the distance over speed limit of each street that you're driving at, and that's taken from the street segment info. And remember, in milestone 1, you had a function that basically you had to implement to get the travel time for each street segment, and we tested for performance. So we want to make sure that it's running as fast as possible, because you're going to keep calling it regularly in this milestone. Plus, so we basically model. Imagine that you're driving and then you stop at an intersection where you're going to turn right or left, but you're waiting for the traffic light. So we're kind of modeling this with this turn penalty. So we're going to pass this, which is just a magic number that we will pass to your functions, and you have to take this into account when calculating the overall travel time. Okay, so imagine that we're driving from, from the source here, which is Cecil and Ross Street, to destination. So there are multiple ways to do this. Okay. First of all, we are assuming. Sorry. Yeah. Go ahead.
Okay. I didn't quite catch the term penalty. So do we have to account for example, direction of turns, because depending on what you
Yes. So the turn penalty will apply for both right and left, but you will have to make sure that you know when you are turning. And we're going to see at the end, but basically, this is easy to model. You're going to check whether the street IDs changed or not. If the street IDs changed, then that means it's a turn, and you have to apply the turn penalty at that intersection. Yeah, make sense? That's a constant defined. We will pass it to you. It's a parameter that's passed to the function. And it can change from one unit test to the other, but as long as, you can consider it as a constant. Like, it's not going to change throughout like the whole program. Yeah, yeah. Okay. So again, we're going to, yeah, go ahead.
Okay, so there's no difference between left turn and right turn?
And we used to do it this way, like we used to like to implement it, to let the student implement either a left turn or a right turn, but it's just more code that is a bit complicated to figure out. So we just figure out, like, just keep it as is. For both left and right, you're gonna apply the same turn penalty. Yeah? Okay, so we are going to be very optimistic about how fast you can go, and we are going to assume that you are driving at the speed limit. Now, most often, like when you're driving in the city, it's not the case because of the traffic, but like we're gonna say that you're driving at the speed limit. So, okay, so in this case, if we're going to from this source to this destination, you have multiple ways to do so. Let's say that you drive 200 meters north on Ross Street, and then you turn right on College and drive another 300 meters, okay? So that consists of multiple street segments. You will collect all of these street segments, and that will constitute your path, okay? Another way to do so, if you drive 100 meters east on Cecil Street, and then turn left, then turn right, and continue to reach the destination. So we can see that there are multiple ways to do so. Now, which one is better? Let's assume that the turn penalty is here 15 seconds. So like it's like an average of what time waiting at a traffic light. Okay. So for the blue path, we have 200 meters over let's say that the speed limit here, we got it from the street segment info that it's 40 kilometers per hour. Plus, we have 300 meters over 50 kilometers per hour. Again, these are assumptions that, let's say, you got it from the database. Okay. Plus, there is one turn here, which is 15 seconds. So that will add up to 54.6 seconds, right? For the red path, you can see that both of them cover kind of the same distance. So 100 plus 200 plus 200, and here it's 200 plus 300. So both of them cover 500 meters. But for the red path, you will see the travel time is 100 meters over 40 kilometers per hour, 200 meters over 40 kilometers per hour, plus another 200 meters over 50. But there are two turns. So there is one turn here and one turn here. So that basically totals to 71.4 seconds. So you can see that there is obviously one street that is better than one path that is better than the other. And that's what we want you to find. Like, can we find the minimum travel time to go from between these two intersections? Okay, so that's for the algorithmic part. Again, there is a UI part in this milestone as well. You will build on top of most of what you did in M2 to find intersections and find between two streets. You're going to use it and build on top of it. So again, this is worth 7%. We require you to do 5 things in this milestone. The first, is my voice so loud? Yeah, okay, because I can hear myself. So first, you have to be able to enter two intersections and find the path between them. This is similar to what you did in my M2, find intersection button. And it should also work with partial street names, etc. But that's not the only thing you can do. You can also click on two intersections on the map and find the intersections between them. So you will have to have some ability to switch between modes where either you're just clicking to get the information about the intersection, like what you did in M2, or you want another way to basically, if we click on these two intersections, you're going to return the path. The third thing that you need to do, once you return the path from the algorithm that you're going to build, we want to visualize this path on the map. So you will have to basically make it clear that for the user which intersection is the source, which intersection is the destination, and how we're going to travel that path. The fourth thing, which is the most challenging part, I think, in this milestone, is to print a detailed guide on how to travel through this path. Okay, and you can do this either on the console, as on the command line, which is basically which will get you the basic feature completed. But we also here mark for usability and aesthetics. So most people basically try to do it on the console, on the map itself, along with visualizing the path. So these travel directions have to be a bit detailed, so and a bit meaningful that the user, any user can understand it, not just people from ECE297. Okay. And finally, we want you to have, I don't think like you did this in M2, we want you to have some kind of a tutorial on how to use your map, or like tooltips on to let any new user figure out how to do things. Okay, so this can be done on the console again, or some kind of a button like that you press on the map, etc. Okay. So these are the basic features, but as I said, your TA will be marking you for usability and aesthetics as well. So to try to achieve that, try to ask your friend or family member to test out your map. Again, we want someone who's not familiar with ECE297 to be able to try and use your map. Is it usable? Is it user-friendly? Is it easy to follow or difficult to follow? All of this feedback is good for you to basically polish your map more and more. Okay, can he or she enter intersections without pain? Like, is it too obvious how to do this or not? And also test on them the travel directions. So let's say that I am building this M3, and my travel directions look like this. I'm gonna say that take street segment number 21, then take street segment number 10. Is this a good travel direction or not? Anyone? Yeah, it's not. Basically, nobody knows what street segment 21 and what street segment 10 are. These are IDs. You can use them for debugging for your own purposes if you're basically debugging your path. But like nobody outside of ECE297 knows what these are. Even I don't know what these are. Like nobody knows unless you dig deep into the database, right? So this is unbelievably bad. Like probably you will get 0 even if you did this, although you completed travel directions. Okay, so let's say we modified it a little bit. Let's say that we did take Young Street, then Young Street, then Brew Street. Basically, I went over each street segment in my path and just printed the street name on that. Is this good or bad? Anyone has any idea? Yeah, B10, go ahead.
I'm assuming you're going over each street segment, which is why you're saying take Young Street, take Young Street.
Yeah.
You could just say like, stay on Young Street until wherever you're turning, but even then, you're not specifying which direction you're turning.
Exactly, yeah. So there are lots of ways to improve on this. So imagine that you're driving, let's say, Young Street is one of the longest streets in the world, right? Imagine that you're driving for like whatever, 5-6 kilometers. For each street segment, you're gonna say, take Young Street, take Young Street, take Young Street, take Young Street. Your map is basically being passive aggressive here. Like you just have to keep going on Young Street. This is also bad. So, but believe me, like a lot of students we've seen in the past do this because they keep the travel directions till the end. They're saying that, oh, it's easy to implement. It's not. Like it's a bit challenging to figure out how to do this properly. So if you leave it till the end and just print the 3 segments, you're probably not gonna get like good marks on it. Okay, so that's why we're saying try to test it on your friends or and family members, because you will want this feedback and you will want to understand whether your travel directions are meaningful or not. Okay, so your friend here alluded to some of the things that you can do. I'm gonna give you around 2 minutes to discuss between yourselves like on some ideas what we can improve in the travel directions, and what kind of ideas we might have to do this. Okay. Okay. I'm gonna ask all of you, like, anyone wants to buzz in on giving ideas on how to do this? Chocolate bar at the end as well. A07, you don't have a microphone yet. Yeah.
Well, a very basic one is to at least specify turning directions
Okay.
beyond just saying the street name.
Okay, so I'm gonna write these here and then we'll show them later. So specify turn directions. Yeah, that makes sense. Basically, if you're going east, say that you're going east, or like you're going to the right, left, etc. Yeah, yeah, go ahead.
Maybe you can also tell them how long before you turn, like let's say like turn in 1 kilometer.
Okay, yeah. So you're driving on a long street, maybe you're driving for 10 kilometers on a highway, you don't know when the exit is coming, so it makes sense that to give them the distance.
Yeah, so you can like merge ahead of time.
Yeah, makes sense. Arnav, go ahead.
I kind of had two ideas. One of them is if, for whatever reason, you can't figure out how to tell if you're turning left or right, maybe it's easier to say turn northbound onto Bloor Street or south.
Yeah, yeah, this is actually important. Like, let's say that you're starting at the source intersection, and let's say that you're at College and Spadina, okay? And then you're going east towards, let's say, College and Bay. So you're gonna say to the user that, oh, drive on College this distance. But they can drive in the other direction, and you have 50% chance of actually going to your intersection, or you're going to throw around it. So if you go give the coordinate directions and go east, for example, it's a bit more meaningful, right?
And my second idea was for, I know that all this they have like key values, and for like motorways and highways, it specifies if you're like on a major highway or if you're on like and it'll tell you there's like an exit ramp as well. So for example, if you're like on the James Gardner, turn left, turn right, doesn't really have a
Right.
say take the exit ramp on.
Makes sense. So yeah, so figuring out where you are in the city actually can help you as well. So if you are on a highway and you're trying to go into the city, basically you're exiting off the ramp, you're not just turning right. So you can also, you can polish by saying take a sharp right, take whatever exit. All of these are meaningful. So data from polishing. Anyone else? Yeah, go ahead. Sorry, speak a bit louder.
Can we send the routing data to ChatGPT and request for an instruction?
You can do that. I'm not gonna, like, if you have an API that is hooked to your map and you can do that, that's actually a good feature. I won't say no. So, yeah, show it to your TA and then we'll decide. But I think it's a good idea. Yeah. Go ahead. Yeah, done.
Oh, can you explain what you meant by before when you said like a 50-50 chance, like how using northeast southwest is better than left or right?
Yeah, I'm gonna talk about that in a little bit. Anyone has any other ideas? Go ahead. Yeah. I'm noting these down and then I'll show the screen. I'm just writing them on the slide. Yeah. Okay. Yeah. So yeah, we said basically specify turn directions, specify the distance to go to how long you're traveling on each street. Use the cardinal directions. Why? Because that's for you done basically. If you are driving from a source to a target destination, and then you're starting at the source, you will say to the user that drive on the street whatever this kilometers. Okay. So there are two possible ways. Either go let's say you're driving east or west. So you either go east or go west. Without figuring out the cardinal direction, you have a 50% chance of actually going in the right direction, right? Like, because you can drive 2 kilometers on College going west, and you can drive 2 kilometers going east as well, right? So we cannot figure out, the user won't be able to figure it out unless you tell him to go east, for example. Does that make sense?
So are you saying that like at a source we need to specify if we're going, like it's a north-south street, we specify going northbound?
Yeah. So this is only important at the source destination, at the source intersection, sorry, because you want to tell the user where to start, right? Once you figure that out, it's easy to go right, left, figuring out what to go, how to go, okay? And yeah, as Arnav said, you can also figure out like where you are in the city, whether you are on a highway, whether you are on a minor street, and say that you can take an exit, take the ramp to go on the highway, etc. Other useful things that you can do also is like showing arrows on the while visualizing the map. Okay, while visualizing the path, that will tell the user how to go in at each intersection. And obviously, we didn't try this here, but I think an important one is to use the street names. Again, we don't want street IDs showing up in the travel direction that nobody knows what these are. So, and there is one minor thing. Let's say that you calculated the travel time on the intersection, on some street segment, and it turned out to be 555.5555 meters. Is that a good travel direction to tell the user to travel 4.555 meters? That's actually going to be overwhelming. They're going to be so stressed while driving, you don't understand like when to turn. So try to round these up, basically, or down, depending on how you want it. Okay, so as I said, the basic feature is to write these travel directions on the console, but it might be better and nicer if you can integrate this somehow into your UI. So visualize it similar to what Google Maps does. They basically visualize the path along, and next to it you can see the travel directions. So if you can do that, that's actually better marks. That's nicer and aesthetically more appealing to the user. So yeah, think about the possibility of doing that. Okay, so as you can see, there are a lot of parts moving on in this milestone. There is an algorithmic and there is a big UI part. So start early, don't leave it till the end because it's going to be very, very stressful. You have around 2.5 weeks from now if you haven't started already. So, and plan to divide the work from now. I don't think this is a good milestone to do like a pair or triplet programming where you can just all sit on one computer and try to do it because it has a lot of parts. But it actually has a good way of dividing the work in parallel. Okay, so anyone has any ideas how to do this? Like if you're going to work with your teammates, how you're going to divide the work? Yeah.
Yes, when I was on my team, I guess, kind of split up into 3 different sectors. Like one person would work on, like focus on the UI and usability aspects of it. And one of our teammates has more experience with like algorithms, so they're going to take on the majority of the algorithm work.
Yep.
And one person is kind of like fixing up the issues that we have with them to getting them out to go faster.
Yeah, that makes sense. So yeah, the easiest part to do this is to split the algorithms and the UI in parallel, okay? Let's leave the third person for now. So one person is working on the algorithm, one person on the UI. Now, one thing about the UI is that you have to write you have to write code to do the travel directions. But can you wait for your teammate who's doing the algorithms to finish to finish the algorithm so you can get the path and then you start working on the travel directions? Or is there something we can do here? Anyone has any idea about this? Like how can we prefetch the paths so that we can start working on the travel directions early on? Yes, Dante.
So if you have an idea of how the algorithm will spit out the resulting data, then you can just create some arbitrary test data in the same format and you stick with that to just test your UI.
Yep. So basically you can start writing some basic code that will give you like some random path between 2 intersections. Just make sure that the 3 segments are connected. It doesn't have to be the minimum travel path, just any random path. And hard-coded, so you remember in milestone 1 when we did when we gave you the skeleton code, we stubbed out all of the code and just returned random values so that your unit test can run. You can do that with this as well. Assume that the algorithm is already implemented and just return any path from that function and use that function to try and draw the travel directions. Try and visualize the path first on the map and then try and figure out the travel directions. So you start with some small path and then you make it bigger and bigger and try to polish it more and more until you are satisfied with the results. This way you don't have to wait for your teammate to finish all of the algorithms because that might take time to optimize and make sure that it is functionally correct. Okay, so again, the UI can be divided into 2 parts. One is the text and mouse. Make sure that you can specify the intersections that you want to travel from and to. And then the other part is the output, the visualization and the travel directions. As Dondi said, basically hard code the path to test before the algorithm even finishes, so you don't have to wait for your teammate. And the third part is the algorithm. Even that can be divided, so some people are more comfortable with algorithms, so they will take on the how to optimize the CPU time for these, while some people will just write a basic approach to just try and find a path. You can try the slowest algorithms. We're gonna talk about a lot of algorithms in this lecture and the next. So yeah, you can divide that as well. You can also divide the coding and testing. So you can start with a basic approach, let someone else test the code, make sure that it's functionally correct. It's at least we have something working, while in the meantime, the person who is coding continues to optimize it. Okay, so that's it regarding the UI, planning and how to attack this milestone. Now it's time to talk about the algorithms, which is the most fun part of this milestone. Okay, so just to remember, basically we are giving two intersections and we want to find the most optimal path that would achieve the minimum travel time going from the source to the destination intersection. Okay, so if you can see here, like let's say I put this on Google Map, I'm going from King College Road to Canada's Wonderland, and there are multiple ways to do this. One is taking 56 minutes, another way is taking 46 minutes. So we want to return the most optimal one. Okay, so similar to how the city is modeled as a graph, we're going to use this graph to try and find that minimum travel time path. Okay, so remember, we are modeling the city as the nodes as intersections, and the edges are basically the street segments connecting those intersections. And in our algorithm, we'll basically try to find, we are given one intersection or one node in the graph, which is the source, and another node in the graph, which is the destination, and we're trying to find the path. What is a path here? It's a sequence of connected edges or connected street segments and nodes from source to destination. So there are, in this case, there are multiple ways to do this. So you can go from this way with the red, oops, or you can go left and then go north, okay? So, but how do we store the path? What is the best way to store the path here? Anyone has any idea? Sorry? A vector of what? Yeah, okay, so the best way is to do a segment IDs. Some people might say that, okay, I'm gonna store a vector of nodes. It might be good, but it's not gonna work perfectly. Yeah, go ahead.
Why don't you do like segment, I mean vector intersection?
Yeah, vector, that's what I'm talking about. Vector of intersection IDs or vector of the nodes in the graph, it can work. So if you specify them one by one, it can work. But there is only one tiny problem in this, okay? Imagine there is a back lane here, okay? So there are two edges connecting the same two nodes. If you're relying on the intersections themselves, you won't be able to figure out which street segment you're gonna travel on when you come here, okay? So maybe this is shorter than this, but because we don't have any idea how to travel from this, we're just gonna randomly choose this, right? And then we'll have a path that is not the optimal one. It's not the minimum travel time one. Yeah. So the sequence of nodes doesn't uniquely describe the path. While if you take the street segments, it uniquely describes how to go from each source to your destination. And because we optimize our algorithm to return the minimum travel path, you're guaranteed to have that. Okay. So now yeah, go ahead, sorry.
So you said when you have two nodes, it doesn't uniquely describe a path, but isn't there only one street segment between any two given nodes?
Most often it is the case, but sometimes you never know. Maybe there are multiple edges connecting these two nodes, right? So it's not guaranteed, like no one can guarantee. Okay, so now let's talk about the algorithm itself. Finding routes, it's actually one of the most fundamental graph algorithms, not just for finding the shortest path. It's actually the building block for any graph algorithm that you're going to face in your career. So it's used in a lot of different applications in some way or another. We're going to talk about a little bit about these applications. So it's very important to understand these algorithms. Okay, so Remember, there are multiple paths possible to go from any source to any destination in the graph, because the graph is not like a tree. There are multiple ways to go from one node to the other, right? Sorry. So do we return any path? What do we mean by the shortest path here? Like, is it just the fewest number of nodes? Is it just the fewest number of edges? Not necessarily. It can kind of indirectly relate to the minimum travel path, but it's not necessarily the minimum number of nodes and the minimum number of edges. Here we're focusing on the minimum travel time. That's what we call our cost metric in this milestone, okay? So this algorithm is a well-known algorithm. It's called the shortest path algorithm in a graph, or the minimum weight path. So usually we add some weight on the edge or the node itself, and while visiting each of the node, we look at these weights to figure out what the minimum path is, okay? So in our milestone, again, the cost is the travel time. So each edge or each street segment is weighted with the travel time that to travel on that street segment. So as we talked about earlier, the travel time definition is the summation of all the travel times for each street segment plus the turn penalty, plus the turn penalty for each turn that you're doing in the path. So remember, in milestone 1, you worked on this part to figure out the travel time for each street segment. And if it didn't pass performance, talk to your TA, because we needed to pass performance. This is very important to be able to actually do a good job on milestone 3. I think most of you did though, but yeah. Okay, so, and then the turn penalty. We talked about this earlier. What do we mean by turn? There are a lot of ways to figure this out. You can do like a dot product, make sure that deflection angle is greater than 0, etc. But we're not gonna go through that. Anytime, in this milestone, anytime your street ID changes, we're gonna consider that as a turn penalty. So let's say that this is the intersection here we're looking at. There are Young Street, there are 2 street segments, and Bloor Street, but there are 2 different streets here, Bloor Street East and Bloor Street West, okay? So if you're going north, there is no penalty, obviously. If you're turning from Bloor to Young, there is a turn penalty. And if you're going straight from Bloor Street West to Bloor Street East, because the street ID changed, we're gonna consider that as a turn penalty. This is way easier for you. You just need to check if the street ID changed. You don't have to figure out whether you are still on the same street realistically or not. And this is also easy for us to test, because there are multiple ways, there will be multiple valid solutions if we say that this is not a turn. And it's going to be hard for us to test it, to test your code. Okay, so I think we still have time. Yeah, we talked about the minimum travel time here in like a GIS solution. Basically, we're trying to find how to drive from one intersection to the other. So that's one application of the shortest path algorithm. But there, as I said, there are a lot of other applications where you can apply this algorithm. Anyone can think of any idea where to use this? Yeah. Think about like other courses, non-software courses that you took, like. Yeah.
For one, Professor Brown talked about like FPGA chips, there's like gates to be able to run them.
Yes, exactly. So in hardware, basically, we want to achieve the minimum latency or the highest throughput of running an application on that hardware. And the way to do this is we always optimize for the minimum latency or like minimum congested route to go from one node to the other. And that's an application of the shortest path algorithm. In Cerebras, for example, we use it as well to minimize the latency, and it's a much bigger scale because the chip is way bigger. So all of these things can be applied. Other applications are internet routing. So let's say that you are trying to ping google.com, and there are multiple ways to go through that because there are routers put different places around the globe, but you want to achieve the minimum latency to go through to the destination route, router, which is google.com, right? And in the back end, there is an algorithm that's based on the shortest path algorithm to try and find that. But in this case, the metric is not the minimum travel time. It's the metric is whether this one node is highly congested or not. So we try to balance the load across all different routers. So that's why we have a metric that measures how much congestion or how much load is currently at each router. Okay, so the nodes will be the computers and switches, and the edges are the fiber cables between these nodes, and we were trying to find a path between these computers. Okay, so again, we can find the fewest routers or the least congested one, depending on the metric that you choose. As your friend alluded to, in FPGA routing, we use this. Actually, in any integrated circuit or circuit design, we use this. So for example, in a circuit board, the circuit board is usually divided into multiple metal layers, okay? And you can connect through these metal layers through what we call vias, which are like these, in this case, edges. So we model this as a graph as well. And each node will be any point in the circuit board that you can connect voltage to. And each edge is basically, if you can go from one node to the other. And if vias cross from one layer to the other, that's also an edge, that's also modeled in the graph. And in this case, we try to find, when we're building the circuit board, to find the shortest path to go from one node to the other. Okay? So this is how we connect chips and IOs, basically. On a larger scale, we use this in integrated circuits, in any ASIC design as well. So it's the same kind of modeling of the graph, but basically this is on a much larger scale. There are hundreds of millions of nodes. So it's very important to achieve a low CPU time on these algorithms and try to find the optimal solution as fast as possible, because it can take you 20 years to actually find a solution if you don't. Okay. Apart from integrated circuits and internet routing, you can also see this in very common things that you use, for example, in social networks and Facebook models, all of the users in a graph. So each node in the graph is basically one user, and the edges will be the friends connecting those users. So like if you have like 600 friends on Facebook, that's 600 edges connected to your node. And Facebook uses that with some kind of a minimum travel path. It's not a minimum travel path in this case. It's some kind of a shortest path algorithm to try and do social marketing. So which influencer should get some money to put some ad on their website that can reach the majority of people. This is all based on shortest path algorithms. Okay, so I hope that gives you a little bit motivation on why we are trying to learn minimum travel paths algorithms or shortest path algorithms. Now we're gonna jump into the actual algorithm. So there are multiple ways to do this. Our first algorithms is probably not a good one to tackle this, but it's very important to learn because you'll probably use it in some way or another in your career. So it's called depth first search. Anyone heard of depth first search before? Yeah. So if you remember binary search trees from ECE294, you learned how to traverse from, let's say, the root to the leaf node. And you do this through recursion. Depth first search is kind of the same thing, but you have to handle cases where it's not a tree anymore. It's actually a generic graph. Okay, so let's say it's a tree right now. So this is your source, this is your destination, and we're trying to go from the source to the destination. So the easiest, we start with a recursion code. So in our main function, we just call the recursive function find path from the source ID to the destination ID. And now we write this recursive function that does the whole thing, given two intersections. Okay. Oops, sorry, go ahead. You wanna? Yeah. So, oops, I should have showed that. So in any recursive algorithms, what's the first thing that you need to do? Yes, base case. Basically, we want to tell the user we want to tell the algorithm when to stop, right? So in this case, when do we stop? Anyone has an idea? Go ahead. I think you have an answer. Yeah. Yes, if we reach the destination. So if the current ID that we are at is the same as the source destination, that means we are done. We can this is a Boolean function. We can return true and say that, okay, we found a path. Okay, if not, then we continue. So we take what the current node is, and what else? What do we do next? So now we are at a current node. We want to traverse down this graph or tree. Let's say it's a tree right now. So how do we do this? What do we do now? Do you have an idea? Yeah, go ahead.
Recursively call the function to like the other nodes connecting to it.
Other nodes connecting to it, right. So remember, in a graph or in a tree, each node has some kind of a children or neighbors in this case, right? So we loop over each one of these, and then we recursively call the function on these. So your new current ID or new source will be the node that is one of these children, right? Okay, so if it is found, we return true. If not, we continue traversing down the path, right? Because if, let's say we are here, and then when we call this children destination, this will return true. So we need to tell this, the recursive function at this stage that the other function returns true. So that's why we have this condition. If it is found, okay, that means my child found the path. I'm gonna return true to the upper level. So we do this over all children until there is no more possible way to traverse. And in this case, we couldn't find a path which will return false. Okay? So let's say that this is numbered as 1, and this is numbered as 2. We try to visit this, okay? And then this has two possibilities, either go down here or go in this direction. So let's say randomly chose 3. We're going to go to node 3. We couldn't find, this return false, but do we return false here? No, because we have to continue visiting all of the other children. Okay, so we go back to 2 and visit now this node, and this node will try to visit the destination. In this case, okay, we found the destination, we return true, and then we return true all the way up. And this is, we found our path. Yeah, go ahead.
Where in the code are you actually like building the path?
Yeah, that's a good point. We haven't talked about this yet. Yes, so we're gonna talk about this in the next lecture. Again, as I said, this DFS is not a good algorithm, as you're gonna see why in a bit, but there are other better algorithms that would give you better complexity and would tell you a little bit about how to traverse the actual path itself. Okay, so what about this graph? Anyone can see any problem with this if we apply the depth first search? Yes, go ahead. Exactly. Yeah, so the problem with depth first search is that you will have to keep visiting traversing down the graph until you reach to a location where you can't visit any more children or any more neighbors. But that's fine in a regular tree. But in a graph, every node might be connected to every other node, so you will end up with a lot of cycles in the graph. So in this case, let's say this is our source and this is our destination. So we go right first, and then we randomly chose to go up, right? So here where the problem lies. So we visit this, and then this will visit this, and then we randomly, because there is a back edge here, we randomly chose that we're going to visit that one. And we keep doing this, right? And this is an infinite loop. Your function won't end. So we have to add some condition to the code in the depth first search to try and fix this. Anyone has any idea how to do this? Yes, go ahead. Just a little bit louder. Right. So we want to basically tag each node whether this node has been visited or not. What kind of data structure that is useful to do this? Do you know?
Like you use struct to represent a node.
Yeah. No, but what data structure you can use to keep track of this? We learned this in one of the first 2 tutorials.
Can you use an order map?
An ordered map, yeah. One way to do this is an ordered map or an unordered set. Basically, your key is the intersection ID, whatever you are. Sorry, go ahead.
Up here, you have your node ID and then a boolean, so that's the location.
Yeah, the value of the map is the Boolean, whether this node has been visited or not. Another way is to do an ordered set. If the node is in the set itself, that means it has been visited. If it's not, then basically we haven't visited. We don't need the Boolean itself, right? There are multiple ways to do this, but yeah, go ahead.
Can you share that method you just mentioned? So I understand the unordered set where essentially your key is the intersection ID.
Sorry, the unordered map, your key is the intersection ID, and remember in an unordered map there is a key and a value, right? So your key will be the intersection ID, and the value is just a Boolean that tells you whether this node has been visited or not. Another way to do this, to just get rid of all of these Booleans, is to use an unordered set. Unordered set is just a collection of nodes that represent a mathematical set, right? So if the intersection ID is found in the set, that means you've already visited this node.
Or just add it to the set.
Yes, it's already added to the set. If it is not in the set, that means you haven't visited this before. You're going to add it to the set now and visit it, right? Yeah. You had a question?
Yeah, if we already created a struct for the node, can we just add a new attribute by indicating whether it is searched?
Yes, but you have to store that somewhere, right? Like,
Just store in the struct.
no, I agree. But like you're visiting multiple nodes in your algorithms, right? And then you reach a random node, you want to get the struct that corresponds to that specific node. How are you going to do that? You want to store all of these structs somewhere. You can use a struct, but you have to use like some kind of an unordered map. Or not. Does that make sense? Yes. Yeah. Any other questions on this? No. Okay, so we're going to modify the code here. Again, as I said, here we're using, we can use also a vector of nodes. And each node has, like, as your friend said here, a struct that is a visited Boolean, right? And we're gonna mark the current node as visited. And then when we visit the edges, or the neighbors of each node, first we're going to check whether that node hasn't been visited. If it hasn't been visited, that means we can visit it next. If we have visited before, then we can just skip it and go to the next node. Okay, so if we apply this algorithm now in the current graph, we're going to go from the source, right, then we go up, okay, and notice here that how we're marking each node here in red, that means we are marking them as visited, right? Okay, then we're gonna come here, we're visiting this. Now, okay, we are visiting this edge, but we notice that this node is currently marked red, which means it's visited. Do you have a question?
Wait, I just have a concern. So, like, do you think the algorithm actually pass as like a variable to the recursive function as well? Because if I think about it, if you make it global, you try one path and like you mark these nodes as visited, but then let's say you try another path, you go up. And then when you go to the right, it already marked as visited, so you don't have any paths.
But that's fine, right? Because if you've visited already one node, right, and you visited all of its children, okay, and then returned false somehow because you couldn't find the path, you returned back, right? And then you came to another path, and then